Hi, my name is Vahan Davoudian. I'm a physics experimentalist for 30 years, and today our topic is optical fibers, which is very important in our life for the communication and everything else. And in fact, this is the only thing can connect all the continents together, and it's so important in our life when we're talking about video, when we're talking about internet, telephone, everything is connected with this fiber optics. And I have to first of all start with this, and then I can show you exactly what I mean by the fiber optics. There's so many details. So fiber optic by Vahan Davoudian, physics experimentalist, and this is my email, vahandavoudian@aol.com. In fact, fiber optic, I have to give you a little bit history, and then I can go in details exactly what do we mean by fiber optics. In fact, I remember because I was, I've been physics experimentalist for 30 years. And then when I started at that time, it was, electromagnetic waves. And now the fiber optic is so important, and the, speed of light is much better than speed of electrons. Anyway, I will explain step by step. So fiber optics is like a conduit. But why do we have light instead of electrons, flow of electrons? The reason why, they travel faster, and the optical fibers are much cheaper, than wires and some other things. And imagine it changed our world. So it's for communication and everything else. And in fact, the good advantage, the main advantage of the optical fiber is, they are not susceptible to electromagnetic interference. But overall, the copper, cables and some other, like aluminum, and they are always susceptible to electromagnetic waves, and there'll be interference. But the light is not going to be interfered anyway. So in fact, this fiber optics is amazing, and then it was invented. His name was Narinder Singh Kopani. He was Indian American physicist, and this was breakthrough in science, and I will explain exactly what it is. So we have a core, and then they are so thin, they're like a human hair, or even smaller than human hair, micrometers, and that's how small they are. So we have a core, and then we have like a cladding which is covering the core. But the main thing is, you have to confine, you have to trap the signals, for the light inside the core, so it won't escape. And in fact, they came up with good ideas, and this is called index of refraction. And then I will explain exactly what do we mean by index of refraction. And like I said, this is the only thing we can communicate now because of being so fast. Well, of course, it's not 100% the speed of light, but it is so good. So fast that is beyond our imagination how it changed our life. Now, before I go in details, I have to explain a little bit about the refraction, because it's important phenomenon in our life, and then it happened in our daily life a lot. But let me take this off so I can put one so you can see exactly what do we mean by index of refraction and some other things. Let me put this up so you can see. In fact, I have to explain a little bit. Mr. Snell, he was a great Dutch physicist, and he came up with this equation. So speed in vacuum divided by speed in medium. Well, of course, it's not vacuum. We're talking about air. But practically, when you divide this, so you get the index of the refraction. What it means, if you have like a straw, or if you put a pencil in a glass of water, you can see it's broken, because when the speed of light is slowed down, or it's just it's getting more and more, the light is broken, and then our perception tells us that that the pencil is broken. So you can see here we have a prism, and then this light is coming in and is diffracted. Well, of course, we don't need to talk about this rainbow now, but you can see it's called refraction. It means that anytime you have an obstacle, especially, you know, like prism, or, you know, it can be something like this, which is a block of, like a clear block of plastic or anything, so we get the refraction. You can see here, this young man is looking at the fish, so this is called, you know, refraction. You can see light is coming here because, you know, air has a low index of refraction and the water has more index of refraction, so it's bending here. And this is very important, angle. This is called angle of incidence. So imagine, I will explain in a minute what happened in fact, he can see the fish over here, but actually the fish is over here. The reason why it is optical illusion, the reason why the fish is not here, fish is over here, because the light is bent. Anyway, Mr. Snell came up with this, speed of a vacuum divided by, speed in a medium. Medium can be like, water, can be glass or anything. So this is the way it works. But, I have to explain why do they use, refraction. Because it's so important in optical fibers. I have to explain this here. See, the light ray is coming in, and this is called the incident angle, and you can see this prism here, and it's getting bent over here, and it's coming toward the surface. But there is a trick that they do with optical fibers. I remember when I was in college, that was called dopant or doping, and that is so important. In fact, if we dope this, if we have a dopant here, what happened, this index of refraction will increase a lot, and finally it will be bent toward the inside, which is called the total internal reflection. What it is, it means that the light is bent inside the tube. I will explain in a minute what I mean by that. Let me see if I have one over here. I can. And this dopant is helping a lot because this is so important. I remember when I studied electronics like 45 years ago, that was called doping or dopant for semiconductor. The main concept is, they have to add impurities. What do they mean by impurities? Because silicon is not conductor. It's a semiconductor. But you know what? Once in a while in a science, we need to conduct a little bit, and those dopant are almost like 1%, something like that, because you cannot exceed that. The reason why we have that is impurity is giving more ions in that, silicon, so you can have electrons to flow a little, not a lot. And if you guys remember, I brought this up in a superconductivity. If you have type 2 superconductor, you can have some impurities, and then that will conduct a little bit, not a lot. So is this here. So if we have more dopant here, that that ray will be reflected completely, and it's called total internal reflection, which is exactly what happened inside the optical fibers. So let me take this off, and then I can show you more pictures for the optical fibers, so you can see exactly how it is to understand. This is a good photo of optical fiber. Let me put this up, you can see. And you can see these optical fibers around the globe. And these are, amazing. You can see those lights because the light is emitted from here. That's why you can see those bright lights. Okay. So you can see the main concept is when the light comes in, it is not going to go, past this boundary. It is not going to go here. It's not going to leak here. But what it is confined, or it's trapped inside the core. And like I said, this core is micrometer. It's like a human hair, or even smaller than human hair. But there is another trick. They have to have something covered. Not only it protected, but this part, which is the core, has high index of refraction, and the cladding has less index of refraction. What it means, this travels much better, and here you can see, because here is reflecting. So what it is called total internal reflection. Why do we do this? I mean, can we do some other things? Like, no way. Because this is the only way you can transmit light so fast. And the main advantage is, the main idea is that you can bend it. And we have in oceans, like millions of kilometers optical fiber laid by the huge ships, and they're still there. They're functioning from 1960s. They're still good, as long as they're not damaged by shark or the fishing vessels. They're still good. So this is the main idea, and I will explain more that how it works. And this is another photo for Mr. Snell, and this was his idea. He was a good Dutch physicist, and you can see this is like the block I have over here. Let me show you. See, this is plastic, but it's a pure plastic. I can show you in a minute. It conducts light so good, and this block over here, you can see here, this block. So the light is coming in, and this is called angle of incidence. So what happened? The light bends, and normally there is a frame of reference here. They call it normal line. So in other words, this is your frame of reference, so you can tell how much the light is bent. So the more you bend the light, so the total internal, the reflection will be less. I show you in a minute. So see, here is reflected here, because air has a low index of refraction and the glass has more. See, the light is bent. So in a simple language, what happened? The speed of light in air is much better than glass. So you can see it's a slow down here. But imagine what happened here. So amazing. It is bending back again toward the surface, and then if you have here something like that, these two lines are parallel. You can see these two lines are parallel. So it's always, the concept is high internal, high index of refraction and low index of refraction for the cladding. And then I will explain, in fact, let me explain this one first. And then I can go more. This is amazing animal, fish. I remember I did this like 6 months ago for the, animals and insects. They are so smart by instinct. And imagine, this fish is one of the greatest, just amazing, because we are the humans. So this is exactly reverse what I said. That boy was sitting over here looking inside the water, but the fish is already inside the water. But this fish can see the insect over here on the branches or something like that. And the nature provided this something for this fish. It's called archer fish, and she is offsetting this, refraction, and this, squirting water, so drops these insects, and then it, take care of them. But imagine, it can be also in reverse. So what this fish does is reversing. But we humans, we're looking from here, and then we can see the fish is over here. But this fish is doing the opposite. So she looks over here, she sees this, but imagine the image is here, but the nature has provided that offset so they can take care of it. But I have to I had to make this so you guys can see how important lens is in our life. I remember optic was my favorite in college, and this was amazing. And this is a good experiment. You can see if I put a light over here, candle or anything, and you can see this sensor, not a sensor, this screen is going to be light. I mean, it's not going to show anything, because imagine this is the light, this is the candle, but how do we know there is a candle here? Let's say if it's completely dark, you won't be able to see it. But you know what the trick is? If you put a lens over here in between, so you can see the lights are coming here, and then this is convex lens, and everything is gathered here, so you can see this upside down, which is the same thing happened in our human eyes. But you know what we can do, the human eyes, brain reverse everything. So you can see here, we can see this, the reason why we have lens over here. So without the lens, you cannot see. For the humans is the same way. Of course, these are nice pictures that you can see this young, beautiful, she's for here. Now you can see our, eye is like a lens. So what it is, the combination of cornea, iris, and the lens is refracting. See, when the light comes in, it's just getting refracted. If there is no lens, she won't be able to see anything. We won't be able to see anything. So in photography, I remember they call it this diaphragm. So you can increase or decrease the light. So this is the way it works. So now I have to show you some pictures for the oceans. It's amazing how, almost 2 billion kilometers in oceans are like this. Let's see, yes. So you can see this is a single, with fiber optics, but I'm not sure if it's the single mode or multi-mode. I'm not sure, but you can see all these continents, they are connected, all of them. Even amazingly, the submarines are moving, but they can have connection. And you can see this picture is better. It's showing all the cables, is connecting all the continents together. And like I said a few minutes ago, as long as there is no damaged shark bite or fishing vessels or earthquake or anything, these cables will last forever, and they're much cheaper than the other things. Okay, of course this picture is better. You can see, let me put this off. This is called the cladding. If you remember, we talked about this a few minutes ago, and this is called the cladding. And then you can see it's just covering, not only protecting, but also it's just confining the signal, so it's not going to go out. But at the same time, they have a lot of protection. They have like coating, and they have that some strengthening, and they have like a jacket. So in other words, it's so strong, nothing can happen. It will last forever. For God knows, maybe 100 years, as long as it's not earthquake, as long as it's not continental drift or anything like that. It's not going to happen anything. And I had to print some of this so you can see what do we mean by single mode. So this is the single mode, and in fact it's amazing. That is called, this is a, 10 micrometer. You see how small it is. It's beyond my imagination how small they are. And imagine, this is a single one, and it is most common used because the attenuation is called attenuation. It means that the signal is not getting weak, is not getting lost because of this. And this one is a graded index. But you can see this is amazing because sometimes the smaller signals are getting lost or getting weak in a single mode. So what they do, they have index of refraction. You can see this part is a little bit a light color blue, so it's just gradually increasing toward the center. So what happened, this light ray is confined in here. This is also multimode, but the graded one are good because they are multifunctional. They can use for long stretch of signals and everything else. And by the way, I forgot something. The new ones, if you can see, in online or on YouTube, not only they have this cladding, on top of this there's another, protective thing, and then on top of that is a copper jacket. It goes all the way. And then I missed something. This is so important. And a few minutes ago I talked about dopant, and dopant is so important. The reason why you need those impurities to add to the optical fibers. The reason why this is the only thing can travel 100 kilometers, which is beyond my imagination how good it is. I mean, how could a signal travel 100 kilometers? So they use dopant for this, and then they just donate some ions. So what happened is they need kind of amplification, and then they get it from those dopant. And like I said, sometimes they use arsenic, sometimes they use phosphorus, but they are so good. And in fact, the biggest companies in the world is in United States, AT&T and some other, and God knows they manufacture millions of kilometer fiber optic with different diameters almost every day. And that dopant, I think, has to do with how conductive this can be. So that is so important. Imagine inside the ocean, there is no way you can have voltage. You cannot get, space. You cannot have a station and then get DC voltage. So everything is provided inside the cable, and somehow they take care of it. This is a little bit technical, but I will explain, because you cannot light something and then let that light go through the fiber. There's so many techniques. First of all, I have to explain that, let me see if I have the electromagnetic waves. I can show you. Let me check. So they use pulses of light. And then it goes through the fiber, because there is no way they can transmit information or the data through the optical fiber. It must be pulses of light. And I think nowadays maybe this is a little bit old, because I remember this like 19, 20 years ago. They used 1550 nanometer laser diode. And in fact, I forgot to tell you, laser is working with optical fibers most of the time. But my next project is going to be laser. But this is the laser diode. They use it, and this generates short pulses. But I have no idea, how they are, how many, few seconds, nanosecond, I don't know, because that's beyond my, expertise. And this special diode is, acting like, generating those small pulses, so that pulses are going through the cable. So light emerging from the laser diode is focused into an exposed core of the single mode optical fiber. When the light emerges, is gathered by the receiver's photodiode. As you can see, this arrows means photo, so it's a photodiode. So that's a long process, but like I said, overall it's more economical than the others, than the normal current. oh no, I don't want this application. I can do the applications later. Yeah. Let me do this one. Let me do this one first. Application, I can do it by the end. See, optical fiber single mode has a high data transmitting in a long distances and the most widely deployed optical fibers in the world. They are strong, flexible, stronger than steel. They do not corrode, rust, or lead in the oceans about 2 billion kilometers. This is amazing. There is no way you can have like a copper or aluminum or some other things. They corrode, they snap. But this, I mean, they are so strong. I can see there was a company, they were showing huge spools. We talk about millions of dollars, and they are so strong. You cannot snap them. There's no way. That's why they, get them for the optical fibers, because they last forever. It's a once in a lifetime. You put it in the ocean, and they last forever as long as they're not damaged. And then I just a few minutes ago I talked about attenuation. This is a special term. It means that the signal loss along the length of the fiber. What it means, there must be so many things that can cause this. Lights get dimmer and it travels in fiber. So quality of glass is so important. What they do, they use plastic, most of the time, especially the purest. I mean, it must be purity 100%. I'm not talking about 99%. It must be 100% the pure, and then they just use that. And then I have no idea how do you add that strength. And like I said, they were pulling so good, they could not snap it because it was so good. So one of them is attenuation, and then the other one is dispersion. Dispersion means due to different, spectra or wavelength. If they have, each one has a different, some lights have different wavelengths. And then the third one is micro bending and macro bending. Sometimes, you can see the optical fibers, they go, let me see if I have one over here, I'll show you. See, these are the fibers. Well, of course, these are so thin. You can bend them, but it doesn't matter. The light goes through. Let me light this on. See, it doesn't matter. If I bend it, the light goes through. See, it doesn't make any difference. But as long as I'm not kinking, or as long as I'm not breaking, it's going to go through. See, it doesn't matter. The light goes through. But sometimes I remember, those old days, electromagnetic interference could be stopped by, like a pure iron or, something like this. So they put it on the, if you have like a small adapter or something like that, they put this. So everything this is called shielding. So what it does is getting the electromagnetic interference. But in the case of optical fibers, we don't worry about that because it is not going to happen at all. But I have to demonstrate this. This is the only way I could do it. I have a laser light like this, and this is the only way I can demonstrate for you. And imagine if I have a light like this, if I have a block like this, it can be glass or it can be, see? You can see here, it goes through. But you know what? This is the angle you can see here is like 90 degrees. And if you remember, I said angle of incidence. So if I increase this angle of incidence, what happened? I'll show you in a minute. The light is going to go here and bend. So this is called total internal reflection. See here? See, you can see here, you can see there's like a T shape. And then when I get the angle smaller, see what happened? See what happened? The refraction doesn't happen. But the angle is getting bigger and bigger. See what happened? is refracted back here. So if you imagine this is like a cable, it's round, so the light comes here. As long as it's not vertical, it has a low incident angle, so it's going to be refracted here. And like I said, both dopant and the less angle of incidence happen that that the light traps in between. Okay. There's a common misconception that communication happened with the satellite, but in fact 95% is with the optical fibers, because we have no choice. Even when we have the optical fibers, again we're using electromagnetic waves, but overall 95% is the optical fibers, because they're so versatile, they're so indispensable, and they do the work. And imagine, it is a common misconception that the most global communication is via satellite. In fact, over 95% of international data and the voice transfer are currently routed through the fiber optics cable that crisscross the world's seafloors. Undersea cables are known as submarine cables. Communication cables are fiber optics laid in the ocean floor and used to transmit data between continents. These cables are the backbone of the global internet, including email, web page, and video calls. And imagine it is so fast, it can transfer in a terabyte. Terabyte means we're talking about 12 zeros, 1 billion bytes in a second. It is impossible for the copper papers, things you transfer this fast. So terabyte, like I said, is 1 trillion bytes. Okay. And the application is so important because this is our life depends on this. Optical fibers. Let's see if I have this. Yeah, okay. And imagine it is used in transmission of data. It is used in so many things. Let's see, this is crooked a little bit. It's so many things. And I remember when, before I came to United States, I used to live by a huge hospital that was a state-of-the-art hospital. And then this was in 1976, I think, yeah. And then we became friends with so many, doctors and, nurses and so and so. And it just happened that one of the doctors was a good surgeon. And then we talked about laws of physics, and one time he said, are you interested in fiber optic? I said, what is fiber optic? And then he said, you have to come to the hospital, I'll show you. And this guy was expert in endoscopy, and he was great, scientist. And he showed me that, this is the way we can save humans' life. We can do biopsy. There's no incision. You can come to our hospital, and then we go everything with this endoscopy. I said, how could you see inside? He says, because of, optical fibers. So anyway, we became friends, and then I remember he just told me, are you afraid of blood and things like that? I said, no. I was in army 2 years, I did everything, so I'm not afraid, I can do everything. So he invited me to the hospital, so we went to the hospital, and then he showed me you don't touch anything, you just watch what we're doing, and then you can take pictures. And well, of course, not the pictures, we used to take slides, because he used to teach also in a college, and then he wanted some slides. And then it was amazing. He said, "Well, come over, have a look." I look at that endoscopy. It was a huge device like this, and then there's a knob. You can turn that, turn the light, back and forth, or left and right. And then I could see inside the stomach. I could see inside the thing, and I said, "This is amazing. This is breakthrough in science. I mean, how could they do something like this?" It's because of these optical fibers. So anyway, this optical fibers is playing important role not only in the communication and everything else, but also in humans' life. So let me read this in medical imaging and the sensing application in telecommunication. Optical fibers are used to transmit large amount of data over long distances at a high speeds. They form the backbone of the internet and also used to telephone and some other things. And this is called endoscopy, which I just explained. And imagine with they said, minimally invasive procedure. So imagine when you go to the hospital, you don't even feel the pain because that fiber optic is so, flexible. It goes inside your stomach, intestine and all your body. And then at the same time, the doctor or whoever is they can check exactly where the fiber is. And then surgery, and then just it revolutionized the surgery with this equipment, and they can also detect the structural defect in the breaches and monitoring traffic flow. This is a picture what I explained for the hospitals. I used to go, and well, of course, this is a simple picture, but you can see a few minutes ago when I explained, the light is coming here, and then it's not getting refracted. But see this angle, this must be like 35, 40 degrees, but this angle is 90 degrees. You can see this is getting total internal reflection. This is exactly what we want. If you consider this like a, fiber optic, light goes through. And there is no way that this is going to be interrupted. Like I said, sometimes it leaks. As long as it's not kinked, as long as it's not broken, it's going to work forever. See, I have another picture here. So it shows the cladding, which is the protective, and this is high index of refraction, low index of refraction. Well, of course, this is multimode, it doesn't matter. But you know what? The light goes through all the way. And like I said, here they have, laser diode, and then here they have photo detectors, and then they do that. I remember when I was in photo finishing before I came to United States, we had a splicer, and the splicer was for the 8mm film. And then I saw documentary in Science Channel, and they were doing exactly the same splicing with fiber optics, but it took them like 1.5 hours because the precision was 100%. But what they did, they had to weld that. They had to heat it up because there is no way you can connect two fiber optics. They're so little, you can't even see them sometimes. So they had to weld them together. So they did a good job, and they connected, the submarine cables to something else. I have no idea what that was. But I just missed something. I remember when I was in college, and my favorite subject was Modem. And then Modem has been around like in 1960s, I think. Yeah. What it is, it's a modulator demodulator. I remember when I was so young, at that time I used to work with a multimeter. At that time it was analog. But nowadays, it's hardly, I had to pay like $200, $300 and buy from Amazon, old one, not even new one. Multimeter, this was not digital. That was the old type because I love those. So the same thing happened. So modulator, demodulator. And imagine the signal is coming from somewhere. We have no idea what it is, electromagnetic or whatever. So we have to convert it back so it will be understandable for us. The same thing happened. I mean, if there is a modem, if there is no modem for the optical fibers, there is no way they can convert it. So because nowadays our life depends on zeros and ones. And then if you, well, of course, I don't want to make a big deal out of it. If you have like 0001 and then 0002, that means hi. And then 0000 something, it means my. And then 00 something name is. So these are, everything is, like a Morse code, exactly, I would say. Morse code was like 250 years ago, but it's almost like that. So it's a binary code. And I remember when people, were asking us, what you guys are doing in electronics? I said, you know what? We are chasing zeros and ones. They would laugh. Well, of course, it is true. We were chasing zeros and ones. And then imagine the reason why I could fix the computers at that time. I was so young because, I was good. I was so good. I could chase the zeros and ones. Oh, here. There is no zeros, so that's the problem. Low signal, we have a high signal. That signal is broken here, so we have to go back and trace it back to find out where the problem is. So that's what happened. So practically 5.44 billion internet users are now, and globally 146,000 people are using internet daily. It's amazing. Optical fibers can last 25 years. Can you believe? The ordinary, cables, coppers and things like that, they won't last that long. It's impossible. Well, in fact, we have to go back to the old days, and then, everything started with telegraph and transatlantic. When they laid that, they had no idea about the optical fibers, because those days the technology was not like that. And that was breakthrough, the transatlantic, because that, even one word you can send it in optical, in like a telegraph was amazing. But those days, that was the best thing to do. So when they did that, and then finally they realized they can do it for the optical fibers, and now gradually, God knows our oceans are so, congested, and then afraid one day our satellite is going to be so congested in space that we won't be able to do anything, because one time I saw something, it's called the geostationary, like 35,000 kilometers above the Earth. There are so many satellites. The reason why we get the TV coverage, we have internet data, everything else, and it's amazing. It's so crowded, but the synchronization, they are so synchronized. We're talking about a nanosecond. They are not going to collide. They work together, all together, and then once in a while, their life is like 10 years. And that's not good. 10 years, and imagine how many times I saw all this satellite, they have a thruster. And then that thruster is exactly like an airplane, because when they have the enough velocity, and then the centrifugal force and then the gravitational force balance each other. So what happened, that satellite is going around the Earth, and like a space station is like a satellite, international, it's going 90 minutes around the Earth, because otherwise it's going to fall. So those two forces are balancing each other, and it's a conservation of angular momentum. That's what happened. They go around the Earth, and that's what happened. They never fall. But unfortunately for the this satellite, when I compared with the fiber optic, which is minimum 25 years, and like I said, as long as there is no shark bite or fishing vessels or the earthquake or any natural phenomena, they last forever, because nowadays everything is taken into the consideration so good. But for the satellite, there is no way. How could you go in that? Because Earth is not that huge anyway compared to the other things. You can go in 35,000 kilometers above the Earth. They're so congested. But fiber optics is not. And then we can have more and more. And in fact, I saw it documented a long time ago, and the Germans are good in science and technology. I was thinking, Vahan, you did electronic troubleshooting all your life, electricity, and then you were a physics experimentalist for 30 years. What if one cable is somehow snapped? Well, it's not going to snap. One optical fiber. And then I saw the German company, the computer shows that, this optical fiber in, between France and England is snapped. So they had to send a technician, and sometimes I'm not sure how true it is. It will cost thousands or millions of euros to fix that thing. And finally, they tracked it down. They knew exactly where that fiber was snapped, or somehow something could have gone wrong. I'm not sure. So they fixed it, and you know what? That computer was showing exactly when the optical fiber is somehow there's something wrong, the transmission of data is delayed, or somehow is in millisecond or microsecond is delayed. So they know exactly what happened, what caused that, what was the delay. They go and fix the problem. And one amazing thing is that, they're going both ways. They can have from this way, the other way, left to right. But unfortunately, when I analyzed that, I said, Vahan, there is no way I can send so many copper cables in the same cable, in the same jacket. The reason why, they interfere. I mean, it's going to be interference, but you know what? The light, there's no interference. And then they're not corroding, they're not, rusting, and they are not going to get broken because, like I said, they're just so good, they are stronger than steel. And that is the way things happen. And I hope I explained everything, and then I don't know if I missed anything. Like I said, we need the modem to do that, and hopefully my next project will be laser. That's going to be also comprehensive, and then I will cover that, and after that it's going to be color perception. I will analyze everything for you guys, and then I'm hoping today you guys like this, even though it was not real scientific. Maybe I missed some, but if you guys like this video, I was wondering if you can go ahead and subscribe it, because that is great encouragement for me. And most people send me an email, they love my videos for the Doppler, and then before that was the spectroscope, and then before that Michael Faraday's lines of forces, and then they want more videos. And then from now on I decided to do twice a month, so every 2 weeks I will publish the new videos, and I'm hoping I have 25 or 30 more. And then if I come up with something, in fact the other day I came up with nanotechnology, and to be honest with you, I have never seen anyone explained in a TV or in a YouTube. I said, hey Vahan, you better take advantage and do the nanotechnology as soon as you can. So I have to research more to see how important nanotechnology is, why carbon is so important in our life. So thanks a lot for watching, and appreciate it, and I'm glad you like these videos. And if you have any comments or anything, if you have any suggestion, or if you have anything, if you want to correct something, you can email me. I'll be happy, because I always accept the criticism, and if as long as it's constructive, it's not destructive, I will accept it. Thanks a lot for watching, and have a good day.